So I'm pleased to introduce Michael Wehner, who's a senior scientist at Lawrence Berkeley National Lab and a longtime participant in climate change. In fact, he's a lead author on the latest IPCC report, which has been in the news lately about what disasters await us if carbon dioxide keeps going out there. So if you have any hard questions about that, he's the right.
Thank you, Jim. So we're going to talk about climate change and modeling and predicting it, or really projecting it is the proper word. And so I'll review a little bit of the basic science behind it and what we know and what we think is going to happen. And then I'm going to talk a little bit about the computational aspects of these kinds of models and end with a particular example which I think is generic to modeling physical systems in general. So I love this phrase that I heard once from a famous man: climate is what you expect and weather is what you get. I heard this from Ed Lorenz. Ed Lorenz is considered the father of modern chaos theory. He was a very nice man. It was a very interesting banquet speech, actually. And that's kind of key. We'll get to that, why that's interesting. But global warming is a politically contentious topic. It shouldn't be. It's a scientific issue. And the science is pretty well settled on a lot of things. But you still have to, a large fraction of this country and others don't believe in it. They think it's some kind of liberal agenda to take over your lives. That's not the case. I'm going to give you some quotes from the Intergovernmental Panel on Climate Change. This is the report that just came out. It's been in the news. In 2001, they wrote, "An increasing body of observations gives a collective picture of a warming world and other changes in the climate system." So that's a statement that it's getting warmer, not really how. But the next statement goes into that, and it says, "There are new and stronger evidence that most of the warming observed over the last 50 years is attributable to human activities." And those human activities is mainly burning fossil fuels, although other things we do affect the climate as well. In 2007, the IPCC made a much stronger statement. It said that warming is unequivocal, which is a word that means there's no doubt. They had no, they didn't want to have any uncertainty in this statement at all. And so there is none. And this is some of the evidence for it. If you look at this plot in the upper right-hand corner, that's data from thermometers, very carefully quality controlled and calibrated between each station across the planet. And you'll see there's a clear trend in that. There's some uncertainty bars on that, and the trend is much larger than the uncertainty in this figure. Since
the axes are small, could you just say how they have...
Oh, so we've this one only went to 2000. By now we've had about maybe 8/10 of a degree centigrade since the pre-industrial era of warming. Not quite a degree.
And so the left, I just can't read the axis.
Oh, I'm sorry. The left, the vertical axis is a departure from a 1961 to 1990 average of the global mean temperature. And so it was colder than that in the pre-industrial, and it's warmer than that now. And so since the pre-industrial, we've had about 8/10 of a degree centigrade. Now the plot below it goes back much farther. This one has a little bit more expanded scale, and this is what you call a paleo reconstruction, where they go back and use proxies like tree rings and gas concentration, isotope concentrations in the bubbles frozen in Greenland and Antarctic glaciers, and it actually is believed now that this is the warmest time that it's been in the last 100,000 years. And that's because of us. So there aren't any natural cycles that have operated in the last 100,000 years that would make us this warm. There were some in the last couple of million. You go back into some of the dinosaur times, and there were times when the planet was quite a bit warmer than even what we're projecting it to be over the course of this century. And so the global mean surface air temperature is actually very rapidly increasing on geologic timescales. In fact, it's rapidly increasing on human timescales. Over a lifetime, it's substantially warmer. And this is due to these changes in the composition of the atmosphere. And you can see that in the other plot on the lower left, which shows concentrations in the atmosphere of carbon dioxide, methane, and nitrous oxide, which are gases that are radiatively active in the spectrum that comes from the sun. And these can be measured very accurately through these bubbles frozen in the ice in these ice cores taken from very deep glaciers. And you can see that it's all of a sudden taking off. And so this global mean surface air temperature increasing is a fact. And the question then comes, is this warming due to human factors? Is that observation of changes in the composition of the atmosphere just coincidental, or is that the cause? And so that's what we need to have models for. And basically this is a classic signal to noise problem. We have to quantify what the natural variability is. That's difficult because we don't have observations in the pre-industrial era. So we have to rely on models for some of those questions. And then the question everybody wants to know is what's going to happen in the future? You know, is this going to continue? Is it going to get worse? And particularly, and this is relevant to the computational aspects, what's going to happen where I live or about the things that I care about? That's the question I get all the time. And so the evidence for climate change is not just temperature, like I showed you. And in fact, when this first came out this way, the critics said, the skeptics said, you know, oh, well, that could just be one thing. You have to have a consistent story. And so that was a valid criticism, actually, and the consistent story has been built over the last 20 years. And other factors that are self-consistent with temperatures rising at the surface have been observed. You know, there's increases in water vapor. This is measured very precisely by satellites. There's well-publicized decreases in sea ice and in glaciers and snow and rising sea level and ocean heat content. The list goes on and on and on. There's only 10 on this. There are probably 50. And you know, so how do we know this is due to humans? And the theoretical basis is actually really solid. This is really old physics. These guys, Fourier, Tyndall, Arrhenius, and Callendar, laid the groundwork for the basic science that causes this. And basically, they measured properties of radiative properties of molecules like carbon dioxide and water, which are very effective at trapping infrared radiation, so at trapping heat. And in particular, Arrhenius, it was a very interesting guy. In 1904, he asked the question, what would happen to the Earth's temperature if you doubled the carbon dioxide? And his estimate of 4 degrees centigrade is well within the range that the latest and greatest climate scientists have agreed upon as the climate sensitivity of the planet. This is one of the most hotly debated characteristics of climate change, and it's interesting that over 100 years ago, just using his head, Arrhenius came up with an answer that is still reasonable guess today. And so one of the things we do with models to attribute climate change to human activities is what we call fingerprinting. And it's just like a detective story where you use all these lines of evidence. And one thing that we've done is we run the model. With the model, you can control the planet. You can say, okay, I'm going to just change one thing instead of all the things that have changed because of humans. And so this plot that has a lot of colors on it in the upper left is the model with just the greenhouse gases, the carbon dioxide and the nitrous oxide and the methane and whatnot, freons, changed according to what was measured. And this is the response of the atmosphere to that forcing change. And it's a plot averaged over all latitudes as a function of longitude. So the equator's right in the middle, the North Pole's on the left, and the South Pole's on the right. And what we see is that the lower part of the atmosphere warms, and the upper part cools. So it's a very distinct fingerprint. When we look at other things, I'll direct you to the sun, which is the lowest one on the left. Changes in the sun cause a very slight cooling. And that's, you could say, oh, well, the observed climate change is due to the sun, and you just aren't getting enough of the sun variability in there. But in fact, the pattern of the change is very different as well. The sky is relatively clear, so the sun heats it relatively uniformly throughout the vertical dimension. And so when we go to what really happened, what we observed, it looks a lot more like this one in the bottom, which is where we're next to the sun, the lower right, where we've changed all the factors. And in fact, we do observe this, that the lower part of the atmosphere has warmed, and above the tropopause, that's where the stratosphere begins. That's where the tropopause is where airplanes fly, jet airplanes fly. That part has cooled, and that complex fingerprint of climate change cannot be explained just by natural factors. You have to have these changes in greenhouse gases. Projections of the future use these kinds of models that do the fingerprint, so trying to replicate these observables, and then you make some guess about how humans will behave, and project out in the future. And what I'm showing here is something from the AR4, which considered two kinds of scenarios. One where emissions of carbon dioxide and other greenhouse gases was drastically reduced, such that the atmosphere stabilized at 550 parts per million. It's currently at 400 parts per million. The pre-industrial was 275, I think. And then the red plot is a business as usual scenario, where you didn't stabilize. You can see there's quite a bit of difference between one scenario and another. The shaded areas around these plots is a measure of uncertainty. A lot of different models went into these. These probably had about 20. The most modern ones have 40 to 60 different models from different groups across the world. We share this data. You know, both, even though one is lower than the other, they're still a lot warmer than today. So no matter what we do, the future is going to be a lot warmer than it is now, and it's a lot warmer now than it was in your grandparents' time. Let's skip that one. Let's skip that one. And go right to something from the upcoming U.S. National Climate Assessment. These are some plots I made for that report, considering a whole bunch of different scenarios of the future. The ones on the left part, the maps on the left, are from the fourth report, the 2007 IPCC report, and the ones on the right are the more modern scenarios, which is a wider range of choices, is what we considered. And so the one labeled RCP 2.6 is a geoengineering solution where one actually has to cause, quote, negative emissions. You have to develop some kind of technology to take carbon dioxide out of the atmosphere. This one assumed that it would happen in the next 20 years or so. I would point out there's no such technology at scale right now. And you can see that these plots are temperature changes relative to about now. And you can see that in this RCP 2.6 scenario, it's about 2 degrees warmer across the United States for the annual average. The one at the bottom, RCP 8.5, is what I would like to call a no policy scenario. That's where there are no policies globally to reduce greenhouse gas emissions. And you can see it's quite a bit warmer, you know, more than 5 or 6 or 7 degrees really in some parts of the country. And in some seasons it's quite a bit warmer. These are summarized over the United States in this line plot, and you can see, and you probably can't see that line. I'll read it to you. On the red line, the solid red line, is RCP 8.5, and at the end of the century, it's a full 6 degrees centigrade warmer than now. That's a lot. And that is the worst case that we considered at the IPCC. It is not the worst case, because in fact, the trajectory we're on is exceeding the assumptions that went into the development of this scenario. These scenarios were developed around 2005 maybe a little bit earlier, 2005, 2006 time frame for use in this current report. There's a lag between, you know, what you can analyze because the models take so long to run. And so in the meantime, what's happened is that greenhouse gas emissions a lot of which are coming from Asia, are higher than the economists had predicted. Here's one of the consequences. All these futures have a consequence. This is one. It would be the consequence of the plot of this plot here, the A1B, which is sort of a middle of the road kind of reduction. This is a measure of drought at the end of this century relative to the end of the last century. And it's negative values of this index, the Palmer Drought Severity Index, imply drought. If it's -2, that's called moderate drought. -3 is severe drought. -4 is extreme drought. And you can see that this is the normal state in the future, projected by the models. And it's suggesting that the normal state for most of the country, or most of the western part of the country anyway, is severe drought compared to today. That was somewhat of a sobering conclusion. In Mexico, it's actually far worse. The average is about -6 in southern Mexico, so it's much worse than extreme drought. The National Climatic Data Center doesn't have a name for -6. One of the more interesting and difficult things to project is precipitation. Now, temperature is somewhat easy in some ways. It goes up. You know, it doesn't generally go down. There may be a few places where ocean temperatures, ocean circulations change, but over land it always is going up in these future projections. Precipitation can increase and decrease, and so it becomes a more difficult thing to project. And for the national assessment, this report that's coming out May 5th, actually, the President Obama will make an announcement, actually. It's going to be a very high-profile thing you'll read about in the news. And for that report, I changed something that we've done in previous reports, and I'll explain that in a minute. What I'm trying to do is give you an idea of the confidence we have. This is the no policy scenario at the end of the century for the 4 seasons and changes in precipitation. Green, bluish green means wetter, brown means drier. If there's a hatching through it, those lines, that means that it's a high confidence region. So I'm highly confident that if this was the future that we had in terms of the emissions scenario, this is the response of the precipitation seasonally in the United States. And so in the northern states in the winter, it will be quite a bit, and in Canada, it will rain or snow, perhaps, depending on how far north you're at, a lot more. Same in the spring, but in the spring, and then in the southern and southwestern United States and in Mexico, it'll be quite a bit drier. That's a high confidence statement. Now in between, and you'll notice actually in the fall and in the summer, there's a lot of areas that aren't hatched, and in fact, I whited them out. And so if the region is white, and this is the new part, I'm making a statement that I'm confident that the changes will actually be small compared to natural variations. Now it's going to be a lot warmer, but the change in precipitation will be small. And if it's colored and doesn't have a hatching through it, then I'm not making any confidence statement at all. Jim?
So how do the white regions map to the drought regions? It looks like
The drought is caused, that picture of drought is caused by 2 factors, precipitation and evaporation. Warmer, and so what that's telling us is that even though there are regions where in this plot that will have more precipitation, the evaporation increases are larger. So, and then when you get into Mexico where the precipitation is going down, it's also, the potential for evaporation is higher. I mean, there's not enough water, so the evaporation rates actually go down. So one of the things I want to tell you about is that if I just gave you this plot, why would I have any confidence to put these kind of lines in? I could look at the model in agreement, and we do that to give some numbers on this. But I think you really don't have can't make a confidence statement unless you understand what's going on. And I think we do. So these green areas that are hatched are places that will get a lot warmer. Warmer air can hold more water by something called the Clausius-Clapeyron relationship. And so more water the atmosphere can hold more water, and so it does, and so it generally rains more. The relationship is not 1-to-1. it can hold more water. It doesn't rain at the same rate that it holds it. So it will be more humid as well. What about the dry part? Why doesn't it gets warmer everywhere? Why isn't it warmer? Why isn't it raining more in Mexico? And the reason for that is there's a circulation change. The tropics expand. That causes the locations of the major general circulation features of the atmosphere to shift, and so a generally downward subsidence of the atmosphere shifts, and that's causing these changes. You could write a similar picture for Europe, in fact, where Spain and Italy and the southern part of Europe looks a lot like the southwest United States when you make this kind of map, and the northern countries, the northern parts of Europe look a lot like the northern US and Canada. Now we're going to do a movie. For those of you online, this one movie won't work. But this is a plot of temperatures just to show you how things evolve. It's not smooth, it's not uniform in time or space. This is a plot of a movie of the temperature change from the 1980 to 2000 average. So in the past it was colder, so we represent it as blue. Now we're getting into the reference period. In this model, this is one model. This model, an older model, warms more in the south first. They don't all do that. And you can see as you get into the 21st century, it gets quite a bit redder. I think this one goes into the 22nd century as it does, and it gets even hotter and hotter. This was not the worst case scenario. So by the end of the, by the end of the 22nd century, in this model, things are 6 degrees warmer, and then under this scenario. So my thing is extreme weather, and I'm really interested in that because this is what you live in. Lawrence said that climate's what you expect, weather is what you get. Weather is what we live in. We live in the noise. And climate change is the signal, as it were. So how is that noise going to change? And so these are some plots, some eye candy of meteorological eye candy of events. The one in the lower right is Hurricane Katrina. That was a very interesting and severe storm that caused lots of human suffering. The one on the upper right is what we call an atmospheric river. It's really a copious transports of copious amounts of moisture from the tropics to the mid-latitudes. Sometimes the weather forecasters, particularly in California, will call this the Pineapple Express. This one goes over Hawaii. These are the kinds of storms that happen in the Bay Area when it's warm and rains really hard and windy. Another kind of storm we get is represented, that happens all over, but is particularly relevant to California, are extratropical cyclones. The picture on the lower left is one of those. In the Bay Area, when you get a cold storm that's coming off of Alaska, it comes off the Aleutian Low, is a predominant pressure system. They tend to be cold and will snow a lot more. Both of those can have extreme impacts in California, flooding being one of them. But if you don't get them, then you have a drought. And so you have 1 or 2 atmospheric rivers in a season, and that is actually what happened this year to keep us from having a really serious drought in California. Was we had a couple of good storms that were atmospheric rivers. And then the other one is a series of snapshots, the upper right corner. This is a very unusual severe weather event that maintained itself across 5 states and knocked power out in all of them. And so I wrote here, what does the IPCC have to say about extremes, temperature extremes? But actually, this is what I have to say. I wrote these statements. And so it's a little unusual to be in a room on your side and watch somebody spit your words back. And that's what happens with these kinds of very high-profile reports, as you see your work used, and that's actually very gratifying. But so what I wrote was, it's virtually certain, and that's italicized, I'll explain that in a minute, that in most places there will be more hot and fewer cold extremes, temperature extremes, as global mean temperature increases. Now the reason that virtually certain is italicized is that is a coded language that the IPCC developed to convey, basically convey probability in somewhat, in terms that laymen might understand. Virtually certain is interpreted as there's a 99% chance of this statement being true. Other calibrated language they gave us was likely. Likely meant that there was a 2/3 chance that it was true, and very likely, which was a 9 out of 10 chance. And more likely than not, which meant greater than 50%. And so if you look at the IPCC and you see these terms, they will always be italicized, and it's explained at the document that's what these words mean. That's how they're to be interpreted. And so this is a confidence statement. It is a value judgment. In this case, the value judgment was made by me. And then I wrote for an underwrite that an RCP 8.5 is likely, so that's the 2/3 thing, that in most land regions, a current 20-year high temperature event will occur more frequently by the end of the 21st century, at least doubling its frequency, but in many regions becoming an annual or 2-year event, and a current 20-year low temperature event will become extremely rare. And so this is the way this has been phrased is that today's extreme events will become commonplace, at least hot ones. For precipitation, because it's more difficult to project, the statements are not quite as strong. I wrote, globally for short duration precipitation events, a shift towards more intense individual storms and fewer weak storms is likely as temperature increases. So I couldn't use very likely because there's a lot of uncertainty in this. And regional to global scale projected decreases in soil moisture, that was the picture of the drought that I showed you, and increased risk of agricultural drought are likely in presently dry regions and are projected with medium confidence by the end of this century under the RCP 8.5 scenario. So these are rather serious statements, and one of the things to consider is that the scientists that wrote this, that write these, like me, are naturally conservative. And then it's a consensus document, which tends to make these statements more conservative yet. So let's talk about computers. Historically, climate models have been limited by computer speed. They still are. But the situation's a whole lot better than it once was. When I started in this in 1990, modeling groups were trying to do their first intercomparison. This is when we started sharing data between the modeling groups. There were probably about 10 groups worldwide. And they took a whole year to do 10 years of simulation of only the atmosphere, not all the components of the climate, just the atmosphere. And the resolution was only 64 points around the planet and 10 in the vertical. Today, or not even today, 2011, so instead of taking 1 year to do 10, now you can do 15 years in a day, and actually it's quite a bit faster than that on the most modern machines. So typically we run for a century or two. Sometimes we run for a millennium. And the standard kind of resolution in the models for the IPCC 5th assessment report that just came out and the US National Assessment coming out in May is 1 degree, which is about 100 kilometers at the equator. And the atmosphere, the ocean, and the sea, I'll get into this, are all simulated. So it's a far more complicated model. Its fidelity of representing the planet is considerably better. But
maybe you'll get this. How much did the time step change?
Oh, it changes by the current condition. So every time you double the resolution, you have, if you don't do the vertical, because the atmosphere especially is very stratified at these resolutions, so it's kind of a quasi 2.5 dimensional model, as it were. So if you double the resolution, you have 4 times as many cells, but half the time step, so that's 8 times as expensive. So computers have taken us a long way, but they haven't taken us where we really want to go. I think that most would agree that regional climate change prediction will require horizontal resolutions of 10 kilometers. We are almost there. But if you really wanted to do the clouds right, which is the biggest uncertainty in these systems, we probably want to go to 1 kilometer. And my colleagues at the lab and I wrote a paper looking at that and trying to estimate what kind of computer we would need for that. We estimated we need to sustain 28 petaflops, which probably is going to happen, actually, in your careers. So when we wrote that, which was now 5 years ago, people laughed at us. It never happened. But those people were short-sighted, I think. In the ocean, we probably need to go also to 10th 10th degree, which is a 10-kilometer resolution as well. And then we have to make multiple resolutions to assess uncertainty. And current practice is maybe to make 4, 10 is better. My group is doing 50. And here's actually an old result that showed that, that winter precipitation in the United States could be drastically improved by just resolution. My friend would say, how much of this is getting smarter and how much is just throwing machines at it? Because it turns out that throwing machines at it gets you better in performance on this particular metric than looking at newer models versus older models. That didn't make him any friends. The observations are shown in the lower right, and you can see that it's high in the southeast and along on the west coast. And the model at 300 kilometers, that's the one at the upper left, misses the feature in the southeast completely. And even at 75 kilometers, it's too weak, but at 50-kilometer resolution, you start to capture these features. And at 25, which is what I'm running at now, is even better. And then extreme precipitation, which is what I'm interested in. In this case, the metric is the 20-year return value. What the return value is, in this case, is that value of daily average precipitation that you'd expect to happen once every 20 years. Or in a changing climate, really, it'd happen this year with a 5% chance. And these models go 200 kilometers in the upper left, 100 in the upper right, lower left is 50, and the observations, which are at 25. And you can see that, that you're starting to capture these kind of intense storms at 50 kilometers. But you miss them completely at 200, and you really kind of miss them at 100. Oh, we're going to go to the movie now. Please work. So they're big movies. Should have gone to a smaller one. Oh, there we go. So this is an animation of a simulation we've done globally at 25 kilometers. This is the state of the art. There isn't anybody doing longer calculations at this resolution. There are only 4 groups, well, 3 groups that can do it at this resolution. What you see is what looks a lot like weather. This is a movie of the total amount of moisture looking down on the planet. So it's an integral of the moisture through the atmosphere vertically. And you can see I picked this to be during hurricane season. You can see hurricanes. You see a lot of other turbulence processes going along. Some of these are atmospheric rivers as well. The point is that this kind of movie is a lot more realistic than it is at coarse resolution. This is the same movie on the bottom that you just saw. On the top is the same model running a similar period at 200 kilometers. Now, Jim, can you see the difference in the back? Okay, because sometimes if you're really far to back or you need your eyes fixed, it's hard to see the difference. And that's good because it means that the large-scale structures in the coarse model are more or less correct, but the fine detail, the fine weather, is not. There are no hurricanes ever made at 200-kilometer models, and the 100-kilometer models make a tenth of the right number, and they're too big, and they're not strong enough. At 25 kilometers, we're starting to really get there. Okay.
Question, what was the total time period during
That was just a couple of months, but the integration was 27 years. Now we're going to look at an atmospheric river. This is from the same simulation, looking at an atmospheric river. This was done for the Regents, and so you'll excuse the simplicity. The Regents of this university. So the moisture is plotted as the, let's stop it for a minute. The moisture is plotted as the white kind of thing, like right here. Winds are the arrows, and their strength is by colors. And then there's some plots in color, isoplots in color. That's precipitation rates. So let's keep on going. And you can see these storms coming through. And this is what real storms actually look like. I mean, they don't go this fast because this is accelerated time, but they're very long and narrow and skinny structures. And in order to resolve that, we have to have the resolution. And I'm going to stop it right here again. This is a snapshot from this movie showing all these fields, but precipitation is what I want you to look at. What it's saying here is that it's, in this case, snowing very, very hard on the western face of the Sierra. That's what happens in these storms. And then by the time it gets to Reno, you're out of moisture. And that's why Reno's a desert, and the mountains get a lot more snow. They get snow in Reno, but not nearly as much. And this kind of storm, it's going to all snow out before it gets there because of the lifting from the mountains. At 100 kilometers, that doesn't happen. The mountains aren't resolved well enough, so they're not as high. And so the simulated storm would go flying right over it. It'll rain somewhere in Nevada. And so the point is that you get the wrong answer. And so if you're interested in California precipitation, for instance. So I just think that's really cool. And so that's something we showed the regions so that they would have something they could relate to. Oh, and that movie is available here. You also can get both of these on YouTube by searching for my name. Here's some work I'm doing with Pravat, trying to count the number of storms. Originally, I thought I could watch movies and just count them, but you can't do that. That drives you nuts. You'd have to have a machine count them for you. So we have an algorithm to do this. The results from the observations are on the top, and from the model are on the bottom. This is all hurricanes and tropical cyclones from tropical storm strength, which is 17 meters a second on up. There are so many storms, it's hard to see them over this period. So we'll peel off the weak storms and only go from category 1 to category 5. And you can see here there are some good things and some bad things about the simulation. The good thing is the storms are more or less in the right place. They're also more or less at the right time in the year. But there are too many in the middle of the Pacific Ocean, for instance. And in fact, there's not quite enough making landfall in Asia. A similar kind of thing in the Atlantic. They start a little too close to the coast of Africa. But when I first did these kind of calculations, I said it's a lot like the talking dog. It's not so much what he says, it's that he speaks at all. And so now we're trying to teach it to speak a little better. But what's interesting about this model is not only does it make category 1 storms, it also makes category 4 and category 5 storms. And so this is a comparison of the model with the observations again. It makes the right number. They observed is a number of tropical cyclones. Those are the 17 meter a second and greater storms is about 90, and the model makes about 90. For hurricane strength, it's about 50 per year, and the model makes about 50 per year. It's a little low on the Cat 4 and Cat 5s. That right number there would be 15, and we make 8.5. But most models make 0, so that's pretty good. This is, again, to get to the computations. One of the issues here is big data. That calculation produced 100 terabytes of model output. In order to make that plot that I just showed you, we had to process 13. And that's expensive. It would have taken 5 years to do that on my workstation. But Pravat wrote this so we could use 80,000 cores on Hopper, and it took half an hour. We have another one looking at these extratropical cyclones. Those are the ones that form off of the Aleutians and other places. That one we've run at scale on the mirror machine, which is a Blue Gene Q at Argonne with 750,000 processors. We use the entire machine. And so these are really interesting, big data, large scale problems. Not the simulation, but the analysis is now becoming the most challenging part. And it's taking me longer to do the analysis than it is to do the simulations themselves. So I have only a little bit of results about what the model says about future hurricanes. I don't have a realistic scenario. I have some idealized 2-degree warmer scenarios. The ones to look at here are the blue and the red. And so in this idealized scenario, the total number of tropical storms goes down. You see that in this part, like all storms. And in fact, the number of category 1 through 3s goes down as well. But the number of category 4s and 5s goes up a little bit. And this would have consequences. There'd be more Katrina-like storms in this world, and fewer run-of-the-mill garden variety storms. But those garden variety storms are actually very important to parts of the world. In Taiwan, for instance, the northern part of Taiwan, if you don't get a couple of tropical storms, you're going to have a drought. And so they need to have those storms. So some parts of the world are adapted to those kinds of storminess. There's some other interesting results. It will rain more in the warmer storms. Again, look at the blue and the red. And that's across all categories of storms that we simulate. And that the category 1 through 5 storms actually will last longer. And so the number of hurricane days is maybe a better metric of tropical cyclone activity than the number of storms themselves. Because if there are more days, then the risk of being exposed to one is greater, and indeed that is the case in this particular model. I'm currently doing some more realistic scenarios. The pattern of climate change may matter even more actually than the amount, and so that's what we call a structural uncertainty that we have to investigate. And, what I want to do is run probably 10 simulations of the future that would be 100 terabytes each, so a petabyte of model output, to try to make a statement about the uncertainty on those numbers I just showed you. So this model only used 8,000 processors, took 5.5 million hours. It's pretty good. The models that we're working on now that the Department of Energy is investing heavily in scales to 100,000 processors. That changes a lot of things. One of the issues in that model is I/O becomes a lot more expensive. The model runs faster. I/O doesn't really change very well. It doesn't scale so well, and so it becomes a larger fraction of the execution time. And so I'm struggling with that now. And arguably machines of order 10 million processors are 5 to 10 years out. And so there's a project that we had that's still going on actually, although I'm not involved, called Green Flash up at the lab, where we tried to understand how we might exploit such kinds of machines. And there's an article here that I think has some results that are not particularly difficult to understand in this journal article here. And that's open access, so anybody can get it. I'm going to say one more result about extremes. Whenever there's an extreme event, you read a lot of hype in the newspapers. And somebody will say, oh, it's climate change, it's killing me. Or somebody else will say, you can't say anything about any individual event in climate change. Both of those statements are false. You can, in fact, say a lot about individual events. While it's true that no extreme weather event that has occurred now was impossible to happen in the pre-industrial times, climate change has had an influence on these events. And in fact, they changed the risk of them. And so what we're trying to do with my group is quantify the change in risk of a given event. And so let's consider 3 events. Heat waves are probably the easiest to try to get a handle on this. There were 3 rather severe ones not too long ago, actually 4. In 2003, there was a heat wave in August of 2003 in Central Europe. 70,000 people died because of that event. Or 70,000 more people died because the epidemiologists talk about something called excess deaths, where they go back and they analyze death records and see a spike in the death rate. And so that's 70,000 for 2003 in Europe, 50,000 for the heat wave in Moscow in 2010. There were also massive fires. That was part of the contribution to those deaths. The air quality was very bad. And in 2011, there was a famous drought that I don't know how many deaths there were, but I don't think those studies have been done yet. But I do know, because a friend of mine's a rancher, that they took cattle to market much much sooner than they would have, because feed was too. They couldn't graze. It was too hot. There was not enough for them to graze on, and so they would had to buy food to feed the cows, and that was too expensive, and so it changed the agricultural economy there. These are very rare events, make no mistake about it. We're interested in how the rarity of these things change. And so we do, we compared realistic scenario, historical simulations, and then a simulation of the world that might have been, where we don't have a human influence, and compare those two. And I'll skip the mumbo jumbo and go right to result, in that that all three of these events, the European heat wave, the Russian one, and the Texas one, were probably doubled in the risk of them happening. This formalism, we actually can give a range, an uncertainty range on that risk, but 2 fits in the middle of each of these estimates of the change in risk. So when that happened, it was twice as likely to happen. So those people that died had some, their death was twice as likely because of human activities. In the future, these events become more common. The relative rarity and because of the climate change isn't uniform, they don't all increase at the same rate. The European one happened earlier, so in 9 years from now, we expect that will be 35 times more likely, and by 2040, 150 times more likely. Basically, there's a plot on the lower left of the probability of this event in an uncertainty range. The median estimate of the probability of the 2003 heat wave happening in any given summer is 90% by 2040. So 9 out of 10 years will be as hot as that year. But these other events, they're more, but prior to 1990, it was less than a line thickness. So it became a rare event will become commonplace in this case. And the Russian heat wave will maybe have a 15% chance of happening at that time, and the US one maybe a 20-25% chance. So this is one of my pet peeves, is that the United Nations Framework Convention on Climate Change, the UNFCCC it's referred to, has stated that we need to limit climate change to less than 2 degrees to avoid dangerous consequences. Well, if my family had been one of those 120,000 people that experienced the death, I would argue that dangerous climate change is already here. Let's talk a little bit about how climate change is modeled, because I'm running kind of short. I'm going to end at 2. Okay. So we want to model all the aspects of the climate, and there's a lot of them. This picture's got more than a lot, but probably not everything on it. And so the model has to, it's a very complex, multidisciplinary kind of model with a lot of different subsystems in it. And so it takes a lot of people. And so these, 20 years ago, I wrote one myself. You can't do that anymore. It's just, not be state of the art anyway, because modern models are very, very comprehensive. So what's in it? You have a model of the atmosphere. The atmosphere has to model the dynamics, the motion. And then you can't, even at 25 kilometers, you don't resolve individual clouds and whatnot. And so you have to have sub-grid scale processes captured. These are listed there. In the ocean, it's mostly the equations of motion. In the ocean, it's mostly the equations of motion, although one has to do some subgrid scale turbulence modeling. In the sea ice is really interesting. It's not a fluid. It's a plastic, viscoelastic plastic substance. It does move, and it distorts with the wind and the currents being the main drivers of it. It's very interesting, and you also have to do thermodynamics. Glaciers are the latest thing. My colleague Dan Martin up at the lab has written an adaptive mesh code, and we're applying it now to Antarctica. And the issue there is Antarctica is big, and the action is all at the edge. And so you have to you need to resolve, you need to have some representation of the processes in the interior of the continent, but you have to have very fine resolution, in fact 250 meters at the edge of the glacier where it's moving, retreating or advancing into the Southern Ocean. And so that model is currently running at 250 meters around the edge, backing off all the way to 5 kilometers in the interior. And so it's a very interesting model, and I expect that our knowledge of how glaciers respond to climate change is going to dramatically improve in the next 5 years because of these kinds of models.
And it's a 3D mesh?
It's again a quasi two-dimensional approximation. It should be three-dimensional, actually. That probably is, in the 5-year time scale being developed. These were not modeled at all 5 years ago. And so it was recognized that this was a major deficiency. 800-pound gorilla in the room is how I would call it, as I called it. And so funding agencies have stepped up, and there's a lot of activity going on in that now. One has to also model the land. It has energy and moisture considerations, but also the biosphere. And so that's a very complicated and it's still developing area. A lot of that work is being done here on campus through an Ez Feng's group. And then atmospheric chemistry, which is, can be very, very computationally expensive because of stiff equations. And many, many species. The current de facto national model has 28 tracers that for the aerosols alone, if you run chemistry, it has 100 tracers that have to be advected. And so advection becomes the most expensive part of the code. And so there's a large computer at Oak Ridge National Lab called Titan that has GPUs coupled onto the CPUs, and so porting the entire code to the GPUs is not going to happen, but porting advection did, and so that's how they run on that machine. This whole idea of having coprocessors coupled to CPUs is what you probably have talked about this, I suppose, and that is causing us to have to reconsider how codes are designed.
Question?
Yes.
So human effects are spread out across those in there?
Yes. The changes are principally to the atmosphere, which then causes changes in other things. So, for instance, the ocean becomes more acid because it absorbs carbon dioxide. That has impacts. The sea ice melts. It may get darker because of ash being put on it. Same with the land ice, the glaciers rather. The biology can take up more carbon dioxide, but it also can die off because the ecosystem changes. And chemistry, you have all these pollutants and things. So humans influence all of these, either directly or indirectly. So we mentioned a little bit about time step stability criterion. This is the Courant condition. And so that causes you to have an additional factor of 2 every time you go up in resolution by a factor of 2. And so as I mentioned, kilometer scale integrations would take 28 sustained petaflops. I think the world record on a climate model right now is 9/10 of a petaflop. And I'll mention that model actually. It's a really, really high resolution Japanese model running on the K machine. And because it's so high resolution in the Courant condition, they do 24 hours in 18 wall clock hours. So it's not a tractable climate model, but it is efficient. So this may be obvious. Why are they so computationally expensive? I've shown you a lot of stuff, and you got to calculate all that. And it's big science. And that, the time scales in the model are minutes, and we want to run for centuries, and there are a lot of minutes in a century. So it's really quite obvious, I think, once you look at it. So I'm going to finish off with an example of computational burden. And so a simple task, just simulate the dynamics of the atmosphere. Consider that the Earth is pretty much a sphere. And so you discretize the planet and map the equations of motions on it. They're going to be the two-dimensional Navier-Stokes equations, and then source terms. Those are the parameterizations that represent subgrid scale phenomena like turbulence or or clouds or moistures or whatnot. And so the traditional way to do this is do it like your globe in your kindergarten class, where you have latitude and longitude lines on it, and make a grid that way. It's simple, but it has issues, mainly that it's convergent near the poles. It's a polar singularity, kind of duh. It's easy to map the equations of motions on it. Finite differences is often what we use. The current model uses the finite volume approach. But the cells, if you can see that here, if you look at these grid points here, they're relatively uniform, but when you get up to the pole, so uniform not the equator means that at the pole they're long and skinny. If you made them uniform there, then they would be long and skinny in the other direction at the equator. And so that has ramifications for the accuracy, particularly if you're interested in a cross-polar flow. Here's the Courant condition. It basically that the time step has to be less than the grid spacing divided by the maximum wind. The maximum wind usually happens in the jet stream in these models, so it's a couple hundred miles an hour. And as I mentioned, cross-polar flows can often have the imprint of the mesh. And so that's important if you want to talk about how sea ice melts, or why sea ice declines. And one of the biggest sources of error in modeling the sea ice in these big coupled models is coming from the atmosphere. The winds aren't very accurate in this area. Another thing to do was to, oh no, I'm going to skip this. Another thing to do is a spectral transform method. And this was something that was very much in favor until about 10 years ago. And that was to map the equations of motions onto spherical harmonics. And so Fourier and Legendre transforms. And so the resolution is expressed by how you truncate these series. T42 was at that time the common. That was about 200 or 300 kilometer resolution, and it meant it had 42 wave numbers. There are a few groups that use this today, but it was very accurate for what it could do. But the problem is that it doesn't scale well. Now, Fourier transforms scale as in the length of the series squared. Fast Fourier transforms scale as m, the length times the log of m. And very fast canned routines exist if m is a power of 2, so they always were. But the problem is that as you get larger and larger, so higher and higher resolution, you would have larger and larger values of m, and it starts to get too expensive. And there are no parallel FFT range algorithms for very large m, for m that aren't millions, and so it meant that these don't map very well onto highly parallel computer systems. So they were great back when I started when we were running vector machines, and because you could have you could unroll these things onto vectors, but they don't work so well on parallel machines.
So how big is M?
Well, it was 42 in T42. The highest now is this. The one group that still uses this is European Center for Medium Range Weather Forecasting, and they're really good at what they do. And they're running around 1,000 or 1,800 at most, which is around the same resolution as the movie I showed you. But they have had to jump through lots and lots of hoops. But they actually have proven people like me wrong, because we didn't believe you could go that high. But most have not.
Aren't there lots of independent Fourier transforms, so that it's sort of embarrassingly parallel?
I don't know. I don't think so. I don't think so. Well, no, I guess it probably is, but it doesn't go to 10,000 processors. Yeah, it doesn't, in fact, because it probably goes to the m, or maybe m over 2, actually. There are other issues. the one I like to see is the Gibbs phenomenon. It rings. These series can have artificial behaviors, and so this was one. I just randomly looked at a model once and said, okay, what happens in the region of the Andes? And so it rains a lot in the Andes right here, but then there's this column of rain right here in the ocean. That's completely unphysical and a result of the Fourier transform. So they called that spectral rain. These are some of the methods they use. The old model from NCAR used this one-dimensional domain decomposition, so it was limited to that dimension. So it was, I think it was 32 processors, might have been 64. They tried to do some things in the vertical, actually, to get a few more. The European Center uses 3 separate decompositions, and so they do global remaps. Each time they do the Fourier, then the Legendre, and then the local physics. And that's why they're good at this. But there's some other things to do, and more modern techniques, actually. One I like a lot is a icosahedral technique, where you start with an icosahedron, that's this shape on the left, and you bisect each of the triangles. So in this case, you bisect from here to there, from there to there, and there to there, and you end up with this kind of discretization. And you keep on bisecting. And so there are no polar points, but 6 points in each hemisphere. That's these along here, and then this one at the pole have a different connectivity in the cells. And originally that was an issue. It left an imprint on the dynamics, but that has been reduced by several million-fold, and so it's no longer an issue.
So the refinement happens
the refinement happens by bisecting each of the triangles. So in this case, we drew a line from here to there. That's this one here. From there to there, and there to there. And then you did it again. So the original triangle was this triangle here is this one here. And so it's been bisected in the same way.
It looks like there's some elevation change in the face.
Oh, and so yeah. So imagine as a child's toy, and you've actually you pump it up, you overinflate it. So yes, and so it gets more and more round as you bisect.
So each vertex lives on the sphere.
Yes, yes. Yeah, I like to think of it as you take that icosahedron and then yes, right. Or just like the analogy is a child's toy that you overinflated. So it's very spatially uniform, so it has that property. Is ideal for finite difference and finite volume techniques. It's easily decomposed into 2-dimensional subdomains, and so it scales well on parallel computers. And the model I referred to from the Japanese group, they actually have they divided it up, I think 16 times. And that gave a resolution of 400 meters globally on the K machine. Here it is. They ran 9/10 of a petaflop. And I think it's just a little faster in real time now. The connectivity is complicated, and it's not logically rectangular. Most of the people in climate have worked on models that have been logically rectangular, and so that's a bit of the use of index lists is a bit of a challenge. Although there are good techniques for that. And here's an example from the map is just one from the Colorado State model. These guys are running at 4 kilometers on the NERSC system here at Berkeley. Another mesh, and this has become very high profile recently, is the cube sphere. So again, imagine a child's toy that was a cube, and you overinflated it so that it became round, and then you divided up each of the faces of the cube regularly. And so it has 8 special connectivity points right here at where the original corners on the cube were, instead of 10. The grid is logically rectangular. It's not spatially as uniform. And that was an issue until people decided, well, we could actually relax the orthogonality of these cells, and one can make it a lot more uniform. It's still not as uniform as the icosahedral one, but this logically rectangular advantage has made it very popular, and it's used in the model that I'm trying to get to run now for my hurricane calculations, called the spectral element community atmospheric model, and that's part of a large DOE effort. There's also a group at Princeton that uses a similar mesh, but a very different dynamical scheme. And finally, this is actually becoming a little antique now, but I think it's really interesting, is different problems require different solutions. If you're modeling the ocean, there's no ocean over land, so you don't have to model there, and you can exploit that. And so, if the poles were covered by land, you wouldn't have the latitude longitude mesh would be perfect, because you don't have the singular points, and that is the case. In fact, in the southern hemisphere, you have Antarctica sitting right at the South Pole, so you don't have this problem. But at the Arctic Ocean, of course, you do. And so some people some years ago invented an orthogonal curvilinear coordinate transformation that could move the North Pole over Canada or Siberia. And so if you do this very carefully, you can get a very uniform mesh. And in fact, this was an early version of it where they put the North Pole over Canada. Later on, they did even and this is what it looks like in the region. This I think is that 10th kilometer, which is their current state of the art, and it's far more uniform than it would be if it had been over the ocean. But it's still not. It still has a lot of variation in fidelity between this Greenland Strait that's called and out in the middle of the Atlantic. The version they actually run, they actually split the pole into two. I'm not sure if I talk about that, where they put one pole over Canada and another one over Siberia. So that's but it's still done through orthogonal curvilinear coordinates. But this is the Los Alamos group. The Los Alamos group is moving towards a completely different model called MPAS, which don't remember what that stands for, but it's based on the icosahedral mesh, but they've made it variable resolution. And the idea there is that they want to capture details of the coastal boundary currents, like the Gulf Stream or the Alaskan current that comes down here, and so get higher fidelity in those regions and less in the middle of the ocean. So the reason I showed you that is just to take a general lesson about modeling. And it's always a set of compromises, and you can do it, and it's not exact. And each of these compromises would cause different kinds of errors to your solution compared to what you would be able to do analytically, if you could. But you need to take in different factors. What kind of machine you have, what scale you're interested in, both spatially and temporally in our case. What kind of accuracy you have, and then what kind of machines you have. Each of these kinds of meshes have different, and for that matter, different ways of discretizing the fundamental equations, have different ramifications, and so one has to keep those in mind. I think there's a lot of computational science opportunities. Go ahead.
One more question
Yeah.
outside. All the algorithms for the dynamics are just nearest neighbor calculations, so hyperbolic, or something global that has to happen too?
The FFT ones are global.
Okay.
Yeah, but the finite volume and finite difference ones are local. They're not nearest. They may not be nearest neighbor. They may be n nearest neighbors. And the spectral element is n nearest neighbor as well, in ways that I don't fully understand. But the opportunities, I think, for people taking this course as careers is really, really good. I mean, we're moving from petaflop, multi-petaflop peak to the exaflop fairly rapidly. Millions of processors, multi-core processors, so one has to have nested parallelism. Efficiency is terrible in these codes. 5% is considered good. 2% is considered acceptable. And a lot of that is because optimizing codes has not been done, or not been done correctly. And some of the work in this department, I think, could be applied there. This idea of hardware software co-design is this green flash thing that I gave you the paper reference earlier in the talk, is a way we think we need to go, both to exploit lots of processors, but also to make the calculation more efficient by tailoring the design of the processor to be more what we need. Many of the reasons for these low efficiency are that we're only using a limited set of the instructions that are out there. And large databases is something that's happened just very recently. You know, I think I'm going to be making a petabyte over the next year or two. This could easily move to exabytes. And this data, there's more information in this model output than myself or my group can analyze. And so we're very proactive in distributing that data. In fact, if anybody here wants to mess around with climate model data, let me know. And so getting that data out to the scientific community is a challenge. It's being done now largely for the 100-kilometer scale models. It has lots of issues. But there are ways to get that data. Getting the volumes of data that we're producing out to the community is in an efficient way, I think, is a challenge. And diagnostics, the analysis, like I mentioned that, you know, Prabhat had written this hurricane tracking algorithm that exploited hundreds of thousands of processors. We need far more of that kind of thing. So it's still, climate change was called the grand challenge problem 2 decades ago, computationally grand challenge problem. It still is. Large teams are required, both physical climate scientists and computational climate scientists. And I think the path of the future is really clear. We need higher resolution, we need larger ensembles of simulations, longer runs, more studies, quantify uncertainty in these ways. We need better physical parameterizations. There's a lot of effort going on that. I didn't talk about that. And this requires substantial investments in hardware and software. Much of that is happening. I would argue that probably not enough. And just an editorial comment that my daughter didn't like much when I first told her this one, that people of my age have identified that there is a problem, and sometimes the public accepts that, or some portions of the public accepts that. But doing something about it is going to be your generation and your children's generation. And a lot of that may just be adaptation, because it doesn't appear to me that there's any political will to avoid the futures that I outlined at the beginning of the talk. So that's it for me, I think. Oh, here's some websites that have some information. The IPCC is on the top. The other one, I think that it may be even better, is globalchange.gov, which will be particularly good after the release of the third national assessment on May 5th. There'll be a lot of information there. So thank you.
So I have questions. You're welcome. I have a question. So does everybody run in double precision? And is there any thought that, you know, is it worth trying to use less precision?
I think there's a lot of thought that that half precision would work, at least on the output fields. They generally are output in single precision. which is probably more than enough. As far as the calculation itself, they're usually done double precision. There are some indications that some of the dynamics, the equations of motion, need to be done that way, but it's clear that other parts do not. And so that would be a savings there.
Help to decide what could be done automatically in single and double, because it's tedious analysis, to say the least, would be useful.
Oh, absolutely, absolutely. Also, auto tuning algorithms. I think we did some work with that on Green Flash, and when we talked to the group we worked with was at Colorado State, Dave Randall's group, and when we told them about that, they just said, "Oh, that's exactly what we need to run better on the machines that we have." And so, general purpose auto tuning would make a huge difference, and not just to climate modeling. I mean, to other physical modeling other physical systems too.
So we're working on a tool to automatically tune the precision, so that's something we can, between single and double, and just have the fewest possible variables be single as opposed to double, but still give you a good enough answer. So we can talk about that.
Yeah, that would be, might be with one place where we might be able to do that easily. Atmosphere models are really a beast because they're so long, but maybe, and lots of different people have ownership. But the ice model that Dan's working on is owned by Dan, and he wrote it by himself. So, so that might be an opportunity.
So any other?
So, this is working. A large part of the reason I took this class was to kind of stuff that you're doing nested between computation and science. So if we're more interested, say, learning more about modeling, are there courses or what direction? How do we go forward?
There are courses. I'm not on the faculty here, so I don't know them that well, but there are courses in Earth and Planetary Sciences, particularly.
If you want to model, there's many departments that have the ingredients for that. We can have that conversation.
But I can't really oversell the fact that the role of computational scientists in climate science is critical, and this is true in other fields too. But I can certainly speak that many of the advances we've made in the last decade were enabled by computational scientists and their insight and their hard work in exploiting these large machines we have. And that is no way that task is done. There are so many more things to do. There's another question in the back.
I was just wondering, with respect to the previous speaker that we had on Tuesday, he was suggesting that for some of his data, it was worth it to, instead of reading in the data that was saved somewhere on a machine, to rerun the data. That was faster because of having to have less I/O. I was just wondering whether that might help some of the parts of this relation.
I've been hearing that for 20 years, and I still don't believe it. And I have fairly strong opinions. You have to know that. But part of that is because, so this big calculation I did. Well, I've done two. One of them has generated 4 other papers that I did not write. I sent them the data. And so, but I didn't know they were going to write those papers when I did the calculation. And the calculation took a couple of months of wall clock time. And so it just wasn't feasible for me to guess what calculation somebody else is going to do. And for the first calculation that I did, I just finished my paper on that, and I'm distributing data to at least a half a dozen different groups. No papers that come out of that one yet, but I expect that they will. And so, one of the metrics that the people that run NERSC like to use is the number of papers that came out of this supercomputer center. It's a pretty imperfect measure of how valuable these machines are, but it is a measure. you know, they may all be lousy papers. I mean, you know, maybe one science paper is worth 10
I think
other
the
papers. But
right metric is that they use is the number of covers of science per megawatt.
yeah, well, you know, that would be the tail of the distribution, as it were. And so, you know, from my point of view, if I can do a calculation and somebody else can use that and learn something, then, you know, that's like doing the calculation twice, except that I didn't. You know, I did this. I bit the storage bullet and the data distribution bullet, and so. You know, if you have an application where you're the only person that's interested in it, or you're not interested in sharing it, then yeah, that may be a possible solution. But I don't see that. I'm not. You know, there are other people that feel quite differently about this.
So I wasn't thinking about not running the simulation. I was just thinking that at the time that you run the analysis or part of it, that you could have a switch between having to regen the data or having to simulate part of the data.
Yeah, what I'm saying is it's just so expensive to run it that we haven't gotten there yet. You know, when we have a 100 exaflop machine, that'd probably be the case. But that may not happen. That might happen in your guys' career. I hope it does. What's after an exaflop?
Yetaflop.
A yetaflop. Yada, yada, yada flop.
This is sort of a tongue-in-cheek question, but has anybody done a calculation of the carbon footprint of all these simulations?
Oh, I want to do that. I want to do that. It's huge. Climate scientists have the worst carbon footprint of anybody you know. I was in Japan last week. I left on Monday, or week before last. I left on Monday, came back on Friday. I came back last night from Washington, and I leave tomorrow for Austria. So I don't know what part of my carbon footprint is larger, my jet part or my computational part, and I'd like to know. But it's if I took those parts out of my life, I'd have a low carbon footprint because I take the train every day. But no, it is an interesting thing to know, and you may have asked it because you know that the power requirements of future computers is daunting. And I had this conversation in Japan actually with some guy who was presenting some future machine plans in Japan. And I asked him, what's a politically acceptable power rate for a computer center? And 30 megawatts is the number that he said. And that was echoed by David Brown, who's my boss. And a megawatt year is $1 million. So if NERSC were to have a 30 megawatt machine, that means that PG&E would be getting a $30 million check every year from the Berkeley lab. And that seems like a lot of money to me. I don't know about you. It's not the $1 million a megawatt year is the discount. Yeah, no, you and I play more at home. Well, unless you have carbon footprints bigger than mine. But it's an interesting thing. It would be an interesting thing to know. I should do that. It's simple to do, actually, because we know what the power rate is and what fraction of the year's cycle I used.
So one more thing, you talked a lot about grids and resolution, how important that is.
Mm-hmm.
And then you compared the regular finite difference discrimination that you're using to the spectrally accurate FFT
Right.
code that some other groups are using. But
Well, that antique groups use.
Okay, sure. But changing the grids typically makes certain numerical discretizations harder to implement. So for a high order scheme, you'd like to have a regular rectilinear mesh, and you showed the icosahedral mesh.
Yeah, oh yeah,
You showed
yeah.
some improvements, but does that not restrict the methods that you could use? And I guess the question is, what is an appreciable order of accuracy of your methods that you use in your simulations?
Well, that's a good question, a really good question. I'll answer the first part first, that mapping different finite difference or finite volume schemes onto these different meshes is indeed possible, and people do that. The implementations can be quite a bit different, can be quite mesh dependent though. The question about order of accuracy is really interesting. common state of the art is fourth order
in space.
in space. I don't know what it is in time, actually. This ocean model that Los Alamos is developing, MPAS, is only second order. And many of us are taking them to task on that. You know, Paul Ulrich, who is a collaborator of ours and a professor at University of California, Davis, has done some nice work looking at the effective accuracy as a function of order. And for the MPAS, the wave that can be resolved is 12 delta x for this code, for the second order MPAS. So a 25 kilometer mesh would what's 12 times 25? It's 300 kilometers. For the spectral element on the cube sphere, which was another one of the ones I talked about, it's 6 delta x. So, you know, it might be more expensive to do one time step because you've got this higher order, so you have more calculations to do. But the effective resolution is twice as good. And so, you know, that's the trade-off one has to look at. I think that that really, really high order, he looked at this as a function of order, and some of the really, really high order ones, the best that you would get was 4 times delta x. And that's for the full wave, and so you could consider a feature to be half that. So, but that's actually, and that's another thing that affects accuracy is not just that would be on a flat Earth. If you have regions of high topography, the topography can influence the accuracy as well. And so if you're not representing, I should put this picture in. I got this great picture of California summertime temperatures in the model as a function of resolution. And at 25 kilometers, Sacramento is a little bit cooler than Stockton. And that's real because of the delta breeze. And that is smaller than the effective resolution of the model, which in this case was 8 delta x, but is controlled instead by the better representation of the topography of the low spot at the Golden Gate in the coastal range. And so I don't actually know how to quantify that, but it's certainly something we see.
Do you guys experiment with multi-grid methods as well, like multi-scale analysis? This grid, because this is like single scale.
People use those kinds of solvers for in implicit methods. You know, when they have the implicit methods add an elliptic equation, and they'll use multi-grid solvers for that. When we were looking at this green flash calculation, which has one in it, we were afraid that would be a computational bottleneck. And much to our surprise, it was not. And so, because we were worried that we might have to use something other than multi-grid, and but no, it seems to be good.
Which model did the elliptic problem come up in? Was that the ocean or the
That was an atmospheric model. You know, at 2 kilometers. But it's used in a lot of different. It is in some ocean models too that would have implicit solves. So the advantage of an implicit solver is you can violate the Courant condition and have a longer time step. And you damp out the instabilities with the implicitness. You can also damp out the instabilities with filters, and that's been done too. But that usually involves then non-local communications, and so those techniques are not very favorable on highly parallel systems. Although highly parallel systems where a lot of the parallelism is on chip could change those kinds of things too. You know, so if you have, you know, 500 processors on a chip, I mean, you might be able to exploit that. And those are challenges that have not been anywhere near fully addressed. We're over time, but nobody's kicking us. Nobody's kicking us out. Okay.
So if there are no more questions, let's thank the speaker.
Thank you.